Thank you all for coming back. That was very bad of you, to those who didn't. I'm very happy to introduce Mario Heiderich, who is our speaker for the next slot, who kindly accepted to step in. So we have a change in program. Mario is the head of a pen test company called QF53, as you can read there or probably guess. And doing my little bit of online research, I found out that he invented or discovered a problem called mXSS, mutation cross-site scripting, and then turned around to mitigate and talk about it, which I think as a pen test company, that's where you want to be, have your own specific problem and then solve it. Please.
Thank you very much. Can you all hear me? Does that sound good? Yeah, sounds like it. Cool. Thank you very much for having me. My name is Mario. As already mentioned, I'm running the pen testing company Cure53, which is located in Berlin. I'm also giving a lecture at the Ruhr University in Bochum once a year. It's like a block lecture. And I am maintaining a project that is called DOM Purify, which has a lot to do with the stuff that we're going to be talking about today. You might notice that I'm talking quickly, so you need to listen quickly because we don't have much time and I have a lot of content on the coming slides. So grab your seat belts and let's go. Let's talk about cross-site scripting, XSS. Probably everybody here in this room knows cross-site scripting. And it's kind of technically the wrong name. We should call it differently because it does different things. Like, we're not really scripting something across other things. We just usually inject some JavaScript and then the alert pop or the exploit goes off. But we still call it like this because it sounds great. And it's actually a very simple attack if you think about this, because all that it really does is allow someone to modify a website through injected HTML and JavaScript. It technically is not really a website that is getting attacked when we talk about cross-site scripting, but it's someone who modifies the website in such a way that the website helps the attacker to target other users. So it turns the website into an accomplice rather than being attacked on its own. And that might be interesting from a legal perspective, but in the end, we're talking about cross-site scripting when the attacker and the website that is like vulnerable or receptive against those kinds of things together in combination turn against other users and then steal their credentials and steal their passwords from the DOM or modify the DOM or trick them into clicking things they don't want to click, etc., etc., etc. And we know how it works, because it basically requires us to put something in the HTTP request. Here we have a very harmless HTTP request that basically has a user parameter that is filled with a value Karen. And the website says, well, that is cool. I'm going to accept this particular parameter value, and I'm going to echo it. Hello, Karen. I am the manager. And if we want to turn this into actual cross-site scripting, an actual attack, or like the means of turning the website into an accomplice, then what we do is change the string Karen to something that is slightly more shady. For example, the good old script alert1. And if the website is indeed receptive against those kinds of tricks, then it will also echo that particular string, and then we manage to inject something into that website using a get parameter, and then we can take this link, get it across to other users, the JavaScript will be executed, and stuff will happen. And we can do amazing stuff with this particular attack, because we can steal passwords from input fields that the password manager filled, and we get those passwords in plain text. That's epic. We can redirect links and forms to just like submit to somewhere else. Nice. We can also steal anti-cserf tokens and basically remote control what the user would be doing. Or we can install a Monero miner, or we can register a service worker, or do amazing other stuff that is really, really particularly dangerous for the other users of that website. My favorite one is, for example, attacking something like meet.google.com and using the fact that this website is already allowed to use the camera and the microphone and just like start listening on the users via XSS. It always works and it's beautiful. So effectively, you can do whatever you want because you, together with the website as the attacker, you control the DOM, you can put whatever in there, and the sky is the limit. And that's why this attack is both simple, yet extremely powerful. And what we do against that, well, we have to avoid a couple of things. We, for example, want to avoid echoing data that is user controlled just so, and comes in via get, post, or anything else that the user can influence. We want to avoid storing or passing on data without any filtering or sanitization, depending on the situation. And we want to avoid making bad mistakes with filtering, coding, escaping, like do the wrong thing in the right situation and the other way around. Because if we do that, then we might have cross-site scripting, although we tried not to have it. Instead, we should treat any user-controlled content using the right methods. And right methods to be chosen is hard because sometimes you have to do this, sometimes you have to do that. Sometimes you have to escape, sometimes you have to encode, sometimes you have to sanitize. It really depends. So you need to also gain awareness of all those contexts that the browser understands. HTML context, JavaScript context, SVG, CSS, comments, attributes, all that kind of stuff. There is like at least 24 different contexts that we should be aware of that can be exploited. And you should also kind of do due diligence and, for example, make sure that your cookies are configured securely, that you're using the proper HTTP headers, maybe CSP or probably not. And you should be just generally very, very careful with those things. And also be careful with the DOM, because, hey, there is still DOM XSS that comes from different input channels. But in the end, it's about throwing something into the website, then making the website do what you as the attacker want, and then attacking other people with that. So that was pretty much it, because that perfectly describes cross-site scripting. But I still have time, so I have a couple of backup slides, which I guess is good. And let's have a look at the backup, because a little bit, like we have something like 20 minutes left, which is something that we can work with. So let's assume we have a situation in which the developers do all the right things. Like pretty much everything is done perfectly well. Like encoding, escaping, filtering, sanitizing, everything is done the right way. Like we properly secure application against cross-site scripting. Everything that is there in terms of attack surface is properly protected, attacks are being mitigated, and all should be good. But it's not. And that sucks, because like we did everything by the book, but there's still a potential of injecting scripts that will then execute for other users. And we might ask ourselves, like, so how do we deal with that? We do everything right, but it's still wrong. What is happening? And this gets us to the topic of mXSS, Mutation XSS, where something mutates in the browser that first looks fine, and then it hits the browser, and then all of a sudden, it's not fine anymore. And we need to kind of be aware of what browsers are actually doing, because browsers do a lot of things in the background. Browsers, for example, optimize stuff that they get fed. It's because they have to. For example, if you feed the browser broken HTML, then the browser tries to fix this, and only after fixing it through the parser, sending it to the layout engine, because otherwise the browser would crash, or the layout engine would crash, or the browser would be really, really slow. And the browser does this for security reasons, for performance reasons, and just also for convenience, because feeding it something broken forces the browser to think what the user could really mean with that, and then hopefully the right thing comes out. What you could do, for example, to test this out is to take a browser and simply open a text file. And now you might say localhost.test.txt. I have no idea what's in there. Let's hope for the best. Okay, it just says hello. Let's have a look at this particular page. We open a text file and we think, well, the browser opens the text file. Like there is nothing hard with this. But is the browser really opening a text file? Because I don't think so. Let's open the developer tools and zoom in a little bit. So we go to elements and we realize that what is happening is not that the browser is opening a text file. No, the browser is constructing an HTML file that is super complex with tons of stuff that looks like a text file. Even with like the font being formatted in such a way that it's like monospace, and it makes us think that it's a text file, but it's really an HTML file that is just embedding the text. And it's the same for example, an image. Let's open a GIF. And see, here, we don't open an image. No, we construct an HTML page that then at some point embeds that image and has tons of user-controlled content, such as, for example, the image's name. And you can kind of guess that we played around with that and try to find out whether there is injection potential, and in older Edge versions, there was. So we could have a cross-site scripting with an image file name, because the browser overdoes it here and doesn't just render the image. No, it auto-produces a massive HTML file with tons of styles and tons of content, and then puts the image somewhere in there, making us believe it shows the image, but it doesn't. It goes further. So the browser does a lot of things in the background. And it has to, and it wants to, and it can. And we need to be aware of that, because that might mean that there's hidden attack surface. As mentioned, this is all a good thing. So this is not per se evil that the browser does this. And the browser wants to make sure that, for example, badly or hard to parse HTML is being optimized in such a way that the very brittle layout engine can actually deal with it and render it as quickly as possible. And that's a fine thing. But is that necessarily also, and in all cases, secure? Well, of course not, because that's why we're here. And let's have a look at a real-life web application of decent complexity. Let's say we take a web mailer. Everybody knows web mailers, right? Like Gmail or Yahoo Mail or Outlook Web Access, like these kinds of things. What does such an application mostly do? Well, we can state safely that it hosts and harbors very sensitive data. Your emails, your contacts, your password reset tokens. If someone owns your email, you have an actual problem. I'm more scared of someone owning my email rather than owning my desktop PC. I mean, of course, it's like semi-rational, but if someone owns your email account, holy crap, you're gonna be so owned, it's gonna be so bad. But we still trust web mailers. Anyway, it shows us, or it shows the users, a lot of data coming from arbitrary channels. Someone's sending you an email, flip, 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 you log into your web mailer, you have a look, and that's fine. It's all happening in your browsers with your authentication cookies, and you're cool with that. That could be like a mail body, that could be like attachments, that could be a mail in a weird char set, and so on and so on. So the web mailer really needs to kind of do a lot of things that are extremely complex. Parsing HTML mails from anywhere, attachments, char sets, anything really. It's like super complex. But at the same time, it has to be fast, and nice and accessible and reliable and well designed so you know where to click and so on. It needs to work on all modern browsers, which is a real challenge. And last but not least, such application also needs to be extremely powerful because you want to have a rich text editor, you want to have your address book, you want to have extra features, you want to have ads in your emails. Now you don't, but sometimes you have, and so on and so on. So that's a lot of requirements for a web application. And it is really, really hard to write a secure web mailer. And usually people fail, and it takes years to get there and provide decent security for this thing. And since this is such a realistic case, we want to use this, of course, as a target for mXSS attacks, because this is one of the few kinds of web applications where we are perfectly cool with the web application rendering HTML that someone else controls, and that someone else could be anyone. And just like sending stuff in, and you will look at it, you will see it. So, how do we secure this kind of stuff? Well, it's easy. The primary attack vector that is coming is, of course, an email that contains HTML that is controlled by the attacker. And then the web mailer says, well, that's easy for me because I just have to sanitize the content of that email without crippling the actual content, so to make sure no alert pops, but still you can read the text. And that usually works in such a way that the email arrives on the mail server, the web mailer notices, and then the server-side code says, well, let me grab the content of the email, let me sanitize it, let me clean it up, and goes through all that stuff that could be potentially bad, like scripts and events and certain kinds of attributes and so on, and throws them out, and at some point the server says, yep, now it's okay, now I can pass it on in a sanitized form, hand it over to the browser, and the browser parses it, renders it, and the user is very, very happy to see their email. Sounds secure? Yeah, I mean, that's like kind of effortful, but it's not secure because browsers, as mentioned, they need to optimize stuff, and sometimes they optimize just a little bit too much. And when they do that, they actually tend, sometimes, in some situations, if you know what you're doing, turn very safe HTML that on its own would never pop any JavaScript into unsafe HTML. And then the server says, hey, that is cool, that is safe, everything's good. But the browser says, oh, let me kind of optimize it for the layout engine, and the JavaScript executes. That's kind of really, really unfortunate, no? And we want to know why and how that actually works. How is that even possible? So let's have a look. Here's a couple of examples of old mXSS vectors that were spotted initially in Internet Explorer and in Firefox, and that was around the year 2012, 2013. We don't have enough time for like a thorough demo, but you can get access to the slides, you can copy paste those, throw them into IE and see what happens. And in all of those situations that you see here, you will find out that the markup technically is perfectly sane, but once you throw it into the browser turns it into something that is no longer sane. And that's bad, because the browser then changes things, optimizes things. And we recorded 3 different generations of Mutation XSS, of changes done by the browser, of mutations done to the markup. The first mXSS generation, which was basically kicking off the research and mostly affecting IE. The second generation that was capable of not just messing with attribute contents, but actually producing markup out of thin air. I have to show you this one. This is just like too good, sorry. I cannot resist showing you this one. So let's go here real quick and throw this in and hope for the best. So look at this. Here we have the input article with some content inside the XML namespace, and what comes out is a massive contraption that the browser creates, assuming that this is the right way to go. And yeah, of course, this at some point blows up and results in cross-site scripting. If you have questions about those, because it's very technical, hit me up after the talk, and I'm going to happily explain them to you, but we don't have enough time to go through all of these because we want to get to the core of it. And the core of it is indeed to look at the third mXSS generation, because that is badass stuff, and that really hit us hard, especially as someone who maintains a sanitizer like DOM Purify. We are like the primary target for those kinds of attacks. So let's have a look. The third generation of mXSS was discovered roundabout in 2019. And we're going to look at examples that did affect DOM Purify and did produce a bypass, but we looked at this and we're like, that bypass only works if you have a very specific configuration option set, and no one would actually have this kind of thing, so we don't really care, it doesn't really matter. Let's not make a security release, let's just like fix it and be good with it. And I actually thought that because I was very confident and was really believing that this is not a problem. But we looked a little bit closer, and then a little bit closer, and a little bit closer, and it turns out that it was a problem. This is the attack vector. The attack vector basically goes no script, and then inside the no script element we have a P element, and that P element has an attribute, and inside the attribute we have another closing no script element. And that means, of course, that the browser that has JavaScript on and enabled would say, hey, there's a no script element, but I have script on, so I'm just going to ignore the entirety of the content. Whereas a browser that doesn't have JavaScript enabled would say, like, oh, there's a no script element, I don't have JavaScript enabled, so I'm going to parse the content of this thing. Which means the sanitizer who runs in the DOM and doesn't have JavaScript enabled in the internal document that it uses to analyze and sanitize the markup that is coming in, has JavaScript off. So this one sees that thing here. Oh, a no script, parsable content, and a closing no script. Everything is fine. I'm just going to remove the element. Whereas the browser, once receiving the sanitized parts, receives something else, because that browser mode, of course, has JavaScript on, because that's the actual page where the whole thing loads. And that sees like, oh, there's a no script element, and you know we don't really care about this. It starts here, there's just garbage here, it ends here, and whoops, then we have an image element that is all of a sudden roaming free in the DOM and executing JavaScript. So the same browser and the same response basically first looks at the thing and says like, JavaScript is off, that's not a big issue, I'm fine with that. And then it sanitizes it based on that assumption, returns it to the DOM, and then all of a sudden JavaScript is on and the whole thing blows up. And we were like, yeah, but that for DOM Purify only works if you actually manually enable no script elements and put them on the allow list. And no one does that. I mean, why would you do that? Why would anyone do that? Like anyone, especially like large websites that are like very, very, you know, powerful and well secured. And like no one on the planet would ever do that, right? Like permitting no script to be one of the allowed elements. No, no one would ever do that, right? Well, Google did on the index page. And we were like, what? So Masato, who found this attack, he was like, I want to find out who else was researching in this realm. He just Googled his own attack vector to find out if someone else found it too. And then that happened. The alert. So if you don't see it, here it is. And he was like, what? And he showed me, and was like, dude, can you reproduce this? And I checked, and I was like, what? And like we were like blown away. That was ridiculous. He got lots of bounty for that, you can believe that. And we realized this problem is maybe a bit bigger than we originally assumed. So we then, of course, analyzed the code, and we realized that Google, despite knowing better, actually uses inner HTML on their index page. Like, seriously? But yeah, so fair enough. I mean, you can look at the video that Fabian did that is like explaining the whole thing in lots of detail. And you can also look at the code at this particular revision of Google Sanitizer and see what exactly they did wrong. So all those links are here. And yeah, something was telling us that this is like worse than we originally thought. And it got much worse. Because then this was published, and a couple of other researchers, amongst them Michał Minkowski, good friend from Poland, he actually looked at the whole topic and he was like, oh my God, this is like worse than anyone would have ever thought. And for us, it was basically mXSS bypass season. It started in 2019 and it wasn't over until like mid-2020, late 2020. I had lots of sleepless nights. And in the end, he bypassed DOM Purify multiple times, and any other sanitizer as well, of course. And we, in the end, looked at the whole thing, and we identified 2 major root causes. Root cause number 1, predictable changes in markup type force a change of parser. We're going to look at that in a second. And root cause number 2, unpredictable changes in markup type force a change of parser. What does that mean? It means that basically we provoke a situation in which we confuse the browser and say, hey, browser, we're starting with XML or SVG or MathML, and then we're hopping over to HTML, and then we're hopping back to MathML, and then we're hopping back to one thing and hopping back to the other thing, and at some point you're going to be confused, and you don't know anymore in which context you are, and then elements that are harmless are no longer harmless. And that looks like this. You have an SVG element, and this SVG element contains a broken P. It's just a closing P element. And now you might say, well, okay, fair enough, this is probably going to get removed. And then you see like the style element in there, and this should be just a style element, and so on and so on. So this looks kind of sane. But if you learn what the browser actually does, because you would assume that the browser just removes the broken P element, but the browser doesn't do it, because the browser repairs the broken P element, which makes no sense at all, isn't even in the spec. Then all of a sudden you have a context switch from SVG into HTML. Then the browser being confused because originally it was just SVG, 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 everything is in XML context, and now you're kind of switching because all of a sudden there is a repaired, fully functional P element, which of course forces the parser to go back to HTML mode. And that means that the style element is treated differently, and then the style element actually ends here and not just somewhere here in the yonder, and that means that the image tag is going to be free and going to be executing. We confuse the browser to do something that it shouldn't do. And the second root cause is similar. And here we're not talking about predictable changes, because this one we could have seen coming, but we didn't. But we look at situations where elements get removed by the sanitizer or by anything in the DOM, and then the context switch happens. So here we have a situation where we have a no embed element that is filled with an SVG element that is filled with a B element, which is already forcing the parser to switch contexts. And what happens is that once we remove the no embed element, but leave the context intact, and that is what a sanitizer usually does, then of course we change from HTML into SVG, from SVG we change into B. B means we get back into HTML, and that again means that the style element is running in the DOM as an HTML element, which frees the content and gives us XSS. And the problem is we never know what really happens. We never know how the stuff is being used, so we can't, as a sanitizer, look into the future and find out what people are actually doing and intending with their markup. So this was a real bad problem. So this was the outcome of the attack vector, and now there is a lot to take, and as mentioned, you can have a look at the slides and you can ask me questions, and I'm going to explain it in detail, but this is like the gist of it. And now the question is, of course, do what now? What do we do? This is like bad. Because technically we can't fix this, because as the sanitizer, we don't know what's happening with the markup once it's sanitized and being used on the website. We have no idea what the developers are going to do. So, well, technically, we're standing there and we have no control over what happens, and then we cannot really offer security. We cannot really offer sanitization services that are reliable because we have no idea what the browser does internally, in what kind of context it's being used, and so on and so on. And it's not even the browser's fault. It really depends on the business logic of the page. What happens to the sanitized markup? Does it go into an iframe? Does it go into a source doc? Does it go somewhere else? We don't know. And only if we know, we can sanitize properly, because we need to sanitize per context all of a sudden. So that sucked. And this was like one of the vectors that gave me the rest, where I was like, no, like here it stops. That was found by our intern, and he was like, look at this, I have bypassed DOM Purify again. I was like, stop. And the fix was eventually that, in collaboration with Michał, we built new logic into DOM Purify that does like parent node checks and basically grabs the context of the element that is there, checks the parent node, sees if there's a match or if there's any violation of context, and if there's a violation of context, then everything is going to be removed, and if not, then we assume that it's fine. And that works so far, and we're quite happy about this. So now, to finalize this presentation, we can't just like let it stand like that, because this is still like an open leg. This is like a really bad problem that is not really fixed in the core. So we have to do two things. We have to think tactically, and we have to think strategically. From a tactical point of view, we got to make sure that sanitizers are aware of this and that they work better and that more people look into them and find cool bypasses and that they get fixed properly. And from a strategic point of view, we need to say, we don't want to do the sanitizer thing as a JavaScript library anymore, because we can't. Someone else do it, the browser. Oh no, you know what? Not just the browser, the HTML standard. So we got to change the standard. And it took me 5 years to actually get to this point. And it was a lot of lobby work. And actually, it was 8 years, I think, in total. It was a lot of lobby work, a lot of talking to people, a lot of hanging out at conferences, talking to browser vendors, giving them booths, and so on, and convincing them this is the way to go. And needless to say, in the meantime, we still had to do the technical thing and make sure that our own sanitizer is still good, and that we provide the optimal test bed for people and are encouraging research, but we have to also solve this strategically. And it worked, because now there is a sanitizer specification, and we made it into a spec. In 2016, I gave a talk in San Francisco and said, people, take this library away from me. I can't maintain this anymore. This is too risky. Also, if I go rogue, then what's going to happen? There's like 7 million downloads per month. This is going to be really bad if I go rogue. But anyway, we can't handle this. This can't be done in JavaScript. It must be done, but we can't do this. And people listened a little bit. And then I went to Schloss Darkstuhl, like this research camp somewhere in the woods, and I convinced people there. And they were like, yeah, this is actually making sense. Let's think about this. And now in 2021, finally, the work is almost over because we have a spec. We have Google committed to it. We have Firefox committed to it. We have Microsoft committed to it. We don't really care too much about Apple. Sorry for that. But we have a spec. So, and the good thing is that the spec is actually so strong that it will change HTML at its core. So we have more or less commitment from Anne van Kesteren from Mozilla, who's sitting on top of the HTML spec, and they said they will change the HTML spec, and the goal is to have an HTML that upon accessing inner HTML or assigning anything to the DOM will sanitize automatically. And we're almost there. We even already have the names of the methods, like set, save, inner HTML, and stuff like this. So this is happening, and this is pretty big, because from this tiny problem with an alert popping somewhere in your browser to changing the entire HTML spec, well, that took a while and was a lot of work, but we're almost there. So you can look at the spec, you can criticize it, you can write file tickets against it, and so on and so on. In the meantime, we of course still have to keep maintaining DOM Purify. We still have to keep pushing browser vendors to actually do this, but we have an implementation. So Chrome already brings it, and Firefox as well. You still have to turn it on by flag, and next month I think they're gonna remove the flag, and then it's gonna be there by default. That's so awesome. And yeah, and if you're like super bored by this, then in the meantime, thank you. Then in the meantime, please also look at other implementations that give you like a virtual DOM. Look at JS DOM. This is a steaming pile of garbage. It's a cool thing, it's a cool tool, but security-wise, please look at it. There is so many bugs in there, and we can't handle this. People use DOM Purify with JS DOM. It's like, no, don't. But they're like, oh, but it works so great. It's like, But anyway, so there's still like lots of stuff to do and lots of research to be done. But that is it, and I hope I didn't kind of overdo it like too much with the time. Thank you very much.
Thank you, Mario. There were two scary moments for me. One was when you described the problem. The other was when I saw you still had about 40 slides to go. Are there questions for Mario? Please. Yes. Microphone? Yeah.
Thanks. I think it's really great that we have this back in the future. But do you expect that there will be bypasses of the sanitation if it's built by the browser?
Absolutely. And we have them already, but they get fixed, and that's a good thing. And I screwed up the look. There was a couple of bypasses already, but the cool thing is if there's bypasses, then it's no longer some kind of semi-maintained one-person JavaScript library, but it's the browser. And they will and they have to fix it, ideally in one day. So sanitizer bypasses are considered criticals or highs, and they will get fixed as quickly as possible. That's where we want to go.
Yeah. So, but then you just change the problem from maintaining the library to maintaining the browser code.
Correct.
But do you think that the root of the cause, that the mutation is so unpredictable that will stay in the future, and that will be still researched that way on Mutation XSS?
I think it will stay, but the point is that we need to kind of lower the impact, because now we have the sanitizer in the browser, and it's like almost in production. Like you can already use it by turning on the flag, but the next step is to change HTML and make sure that all assignments of strings into HTML elements will also get sanitized by default. And then we have the big advantage that we don't have right now. Right now, we can't look in the future. We, as the JavaScript library developers, we don't know what the developer does with the markup that they sanitized and put in the DOM, but the browser does. Because you put it in the DOM, and in that moment, the browser says, like, oh, there's something coming from, into, this is what I have to do. And then it's sane. And that is like the last mile that we need to kind of that we need to achieve.
Great, thanks.
And then I think it's actually like, we can actually say we have like safe HTML handling.
Okay. More questions, please. All right. So everything's going to be fine in the future?
Absolutely. I guarantee it.
Right. Okay. I think I just saw your nose grow a little bit. But, I mean, where did this start? What got us into this mess in the first place?
Oof, you really want to hear the story?
Whose fault is it?
Deutsche Post?
Okay.
They had like this amazing website that is called E-Postbrief, where you can send emails, but they cost money. And they had like the security challenge, and they wanted to kind of prove to everyone that the system is safe. And we managed to kind of participate in this challenge. And we didn't find anything. And that was like horrifying. Like, it was a web mailer, but we didn't find anything. And then basically a couple of people came together and looked at this whole thing, and then we realized that, yeah, this mutation thing, that works here against this platform. And then we had 1 attack, 2 attacks, 5 attacks, and every attack that we actually deployed gave us 5,000 euros as prize money. So that was pretty cool. And then I went to my prof at the Ruhr University, and he's like, dude, Jörg, we need to kind of look into this. This is big. And he's like, yep, then look into this. And then this is pretty much how it all started. So it was like lots of contributions from lots of people. Some of them are mentioned here. And basically, at some point, it came together in such a way that people were able to realize this is an actual problem. We need to do something about this. And this is where we are right now.
All right. If there are no more questions, we'll finish right on time, despite,
Thank you.
48 slides. Fantastic. Thanks again. Brilliant. There was one more thing I read in your profile. You prefer Belgian chocolate. Ooh. So I'm not quite sure you're worthy, but I think your talk convinced me to maybe overlook it. Thanks again.
Cheers. I'll check it out. Thank you.